Hi guys. Today I thought I'd come online and basically go through a question on specific heat capacity and latent heat. The question says, the amount of heat required to convert ice at 12 degrees Celsius to water at 73 degrees Celsius is 23 kilojoules. Calculate the mass in grams of the ice that is converted to water. And we get given some constants. The specific heat capacity of water is 4,186 joules per kilogram per Kelvin. The latent heat of fusion of water is 3.34 times 10 to the minus 5 per kilogram, and the specific heat capacity of ice is 22,100 joules per kilogram per Kelvin. So the first thing that I'm going to probably write is the fact that water is ice at 0 degrees and below. Okay? So the freezing point for ice, the freezing point for water is 0 degrees. Below 0 degrees, water should be solid. Okay? And then I can write water is liquid water at any temperature that is more than 0 degrees Celsius, okay? And then I'm going to write that water is gaseous water vapor at more than 100 degrees Celsius. So at 100 degrees Celsius, water begins to boil and you get a change of state from liquid to gas, right? Now, all of this information may not be relevant to the question. However, it is a useful exercise in making sure that we are well grounded. So the second thing I'm going to do is that I am going to draw approximately what will be happening. I'm going to draw it. So I have my y-axis and my x-axis, and I'm going to label them energy and temperature. Now I'm going to draw a bunch of straight lines. So I've got a straight line there, 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 got a straight line there. And what I'm going to do is that I'm going to label exactly what's happening in these sections of straight lines, right? So for now, I'm going to assume that we start at the bottom. Okay, we start at the bottom as a solid. And currently what we are doing is that we are heating that solid. As we pour energy into the solid, we are heating it up and raising its temperature. Heat capacity is a measure of how much energy a solid object can store. Okay, and it's a function of the mass as well. So the more mass the object has, the more energy the object can store. It is also a function of the specific heat capacity, an object's innate ability to store heat. So the higher the heat capacity, the more heat an object can store. So for now, I'm going to label this straight line as heat capacity. Okay? So this is me saying to you all that raising an object's temperature is related to heat capacity. So what happens in these sections where there is energy being poured in but there is no temperature change? Well, that is where we get changes of state. So here I'm going to say this is melting, because once we reach 0 degrees, which is the melting point of ice, we have a change of state, and changes of state are described by latent. So this is going to be latent of fusion right there. Okay, so if you're wondering what latent heat meant, a lot of physical terms are very, very intuitive in my opinion. So for example, when we think of latent, we often associate it with latent potential. I mean, think of, I don't know, Dragon Ball Z, right? Where in the earlier seasons of Dragon Ball Z, it was always said, oh my god, Gohan, he's got huge latent potential, and if he should ever release that potential, he'll become stronger than everyone in the universe, and yada yada yada. He was always a disappointment until the Cell Saga. But so in order to change a solid into a liquid, we need to actually break the physical bonds that hold that solid, those solid particles in a lattice, right? So imagine ice. You've got a lattice structure of water molecules, and they are being held together by strong physical bonds. We need to break those bonds. Until we break those bonds, we cannot fully melt into a liquid. So latent heat of fusion describes the amount of energy that is required to actually break those physical bonds. Only then can we fully melt into a liquid and continue heating up the liquid. So now I'm going to continue filling up my graph. This is liquid, and this is another instance of heat capacity. Okay, so I'm heating up the water over time until I reach probably 100 degrees Celsius. So I should also note down here that there are certain temperature barriers here. So if I just draw a dashed line there, and I can just say that that is 0 degrees. And if I draw another dashed line here, I can say that over here we have 100 degrees. Okay, so I've heated a liquid up until its boiling point, and this is where we get latent of evaporation. The amount of energy required to change, to break intermolecular forces in a liquid and allow it to change state from a liquid to a gas. And this is called evaporation. Now these are the 3 states of matter, where now we have a gas on this next vertical line, and again this is heat capacity. Now for anyone in my profession, which is, I spelled that wrong, for anyone in my profession where I'm a plasma physicist, there is yet another change of state, the 4th state of matter, which is plasma. It doesn't really matter for you guys right now, but just because I like to dive in, there's another change of state from a gas to a plasma, and that involves ionization. Now, I'm gonna admit, I don't actually know what this would be called in the conventional sense. What would be called ionization? I just said the word. Changing a gas to a plasma is very specific in that you need to ionize the atoms or the molecules. That takes energy. It takes energy to strip the electrons off of the atoms or off of the outer shells of the molecules. And then you can start heating up a plasma, okay? And there is some measure of heat capacity when you're heating up a plasma. All right, so now we have our understanding of heat capacity and latent heat. How do we use that? How do we use this to answer the question? So total energy, Q, equals heating ice, which I'm going to write as the mass of ice multiplied by the heat capacity of ice multiplied by the change in temperature, to do that, plus melting ice, which is the mass of the ice multiplied by the latent fusion of ice or water, plus heating water. And that is going to be the mass of the water, which is the mass of the ice as well, multiplied by the heat capacity of the water, multiplied by the change in temperature of the water. Okay, and if you're wondering, oh, where are these formulas or expressions coming from, then heat capacity is given by the amount of energy divided by the change in temperature and the mass. So mass times change in temperature, everything under Q, which is energy, and that is heat capacity. So heat capacity C is given by this expression right here. And I'm just going to box that in purple to show that this is an important expression. A similar expression can be obtained with fusion, latent heat, or fusion, or vaporization. So latent heat, but this time I'm going to write it as Q. So latent heat equals the mass multiplied by the latent. The question was asking us, calculate the mass in grams of the ice that is converted into water, knowing that this whole operation took 23 kilojoules. Okay. Now, I am going to multiply these values together and add like terms. So I'm going to add these numbers together. Okay, so that's 23 times 10 to the 3 divided by 6,64778 equals the mass in kilograms, because we're using SI units, we're using the base unit, so we are going to end up getting the mass in kilograms. We have to convert to grams. So 23 times 10 to the 3 divided by 6,64778. That gives us 0.034 kilograms, which is equal to 34.59 grams as our final answer.